So this is roughly how the webinar is structured. We have 6 different notebooks. Um, and as I mentioned, we don't have time to go through all of them. So I'll be focusing mainly on notebook 1, which is obviously the basics, the types of visualizations that you are most likely to use most often. Um, then in notebooks 2, 3, and 4, there are some really, really useful kind of dynamic elements that you can use as a reference. So they're not going to be something that you memorize in your head, but they're really useful to have whenever you do need to produce a visualization. They're really useful to have as reference documents because they really help in customizing visualizations. So I'll just go very, very briefly through some of them just to show you how you can use them. And the idea with that, or my suggestion with that, is for you to keep these files kind of on your computer. And whenever you do need one of those visualizations, just open them up and use them in the way that I will show you. And then in the later half of the webinar, we will look at Notebook 6, where we'll be, instead of using built-in complete visualizations, we'll be building our own visualization type from graphical primitives, again, all while staying inside Wolfram Language's ecosystem. So that's kind of the plan for today. So let's start from notebook number 1. Let me make that a bit bigger and let's get into it. So as I'm kind of introducing the first notebook, I will shoot off a few polls in the big marker chat. Uh, the polls are asking a few questions about your usage of Wolfram language and your experience with the webinars, and they really help us tailor the content better. So when we're thinking about producing new webinars, we always take that into account. So if you could take a second to answer those questions while I'm introducing this notebook, that would be much appreciated. But after that, we are right into the webinar. So whether you prefer to follow with the notebook open, you can download the materials now, or if you just prefer to kick back, relax, and just watch me present, then you're very welcome to do that as well. So let's get into it. So as I mentioned, it's a very beginner-friendly webinar, where we'll be doing visualization. So the first question to ask is, why would we want to do visualizations at all? We all know that Wolfram language is very adept at analyzing data in a very nice way. So in many cases, we might want to just analyze our data, get the numerical or symbolic result out, and be done with our day. So obviously, visualizations carry a few benefits over and above simple numerical or symbolic answers. Visualizations might allow you to get some insights about your data that you wouldn't otherwise get just by looking at numbers or spreadsheets. And obviously, the more kind of the more popular reason for doing visualization is just to communicate your findings with other people. A picture is worth 1,000 words and all of that. So these are the main reasons why we do visualization. So as I mentioned, we have a slew of different visualization types in Wolfram language. So basically, for every data structure you encounter, there will be a corresponding visualization function. So just to name a few: scatter plots, charts and histograms, time series, tables, geographic visualizations, and many, many, many more. In this first notebook, we'll look at the most simple ones, or we'll look at some histograms, we'll look at some line plots, just your most typical kind of visualization types. Before we get into the actual visualizations, let's say a few words about the data that we're going to use. So the data we are using comes from the Wolfram Data Repository, which is an online repository where users can submit their own data. And the Wolfram staff verifies it. And if it is accurate, if it's sourced well, if it's formatted well, then it's published on the Wolfram Data Repository. And every Wolfram language user can make use of that data very easily in their notebook. So as far as we're concerned, the main reason why we're using data from the data repository is that it's already quite well formatted. So one of the common challenges in data analysis in general is that you get some data set, but you need to do a lot of cleaning, you need to do a lot of transforming and so on. And while that is an important part of data science in general, it's not really the subject of our webinar. So because we're looking only to visualize data, it makes sense for us to start with data that is already cleaned up and nice and easy for us to work with. So what is the data about? So it's a data about US baby names by state. So it's a comprehensive list of frequencies of baby names in the US listed by year, state since 1910. And that data comes from the Social Security Administration, which I am guessing is some US government institution. It's important to mention that all of the data you find in the Wolfram Data Repository will have its corresponding source, so you can kind of verify that it is real data and it's not something that someone just made up. So to get the data from the data repository into your notebook, all you need to do is use this resource data function, and that will load the data um, into your notebook without any extra effort. So you don't need to import CSV files, you don't need to download anything. Just call resource data with the name of the dataset, and you're good to go. Um, if you have downloaded the materials for this webinar, then the data will already be included in those materials. If you're just following along in your own notebook, then feel free to run this resource data function, which will download the data for you. The data is quite big. It's about 200, 300 megabytes, but still, it shouldn't be that long to download if you prefer to do that. So let's look at just a random sample of the data, just so we can get a feeling for the structure, and yeah, how the data is structured, what the data looks like, so that when we start slicing it, we know what we're actually doing. So here we're looking at, yeah, as I mentioned, a slice of the data. So you can see we have 5 different columns. We have state, gender, year, name, and number. So basically, the way to read this data set is that in the state of Minnesota, in the year 2015, there were 6 females with the name Gemma. So for each row, you can basically read it like this, and hopefully, in that way, the data makes sense. We can take a random sample of 4, so we can see in the state of Maryland, in the year 1985, there were 37 females named Caitlin, for example, and so on. So this is the data that we'll be dealing with today, and the good thing about this data is that it includes a lot of different types of data. So the good thing about the data set is that it includes a lot of different types of data. So you have state, which is obviously a geographical entity. You have gender, male or female. You have years, which is time series data. You have name, which is just normal plain text. You have numbers, which are obviously numbers. So that gives us a very good foundation to start exploring different types of visualizations. And in fact, it's a very fun kind of data set to play around with. In fact, as I was preparing for this webinar today, I got curious about some aspects of the data, so I was slicing it in different ways, and I was looking. Basically, the question that I had was, because we're looking at names by state, and you can see that some of the names are actually state names as well. So, for example, the name Montana is a name of a person, but it's also a name of a state. So the question that I had when I was looking at this data is which is the most popular person's name, which is also a name of a state, if that makes sense. So I was having a bit of fun playing around with that. So I have the results. If you want to have a guess at what is the most popular person name, which is also a state name, feel free to drop it in the chat or just make a note of it yourself. Just kind of a pub quiz question as we're going through. I'll share the answer probably after this notebook. But if you want to have a guess at that, but yeah, just in general, it's a very nice and simple data set that you can use to practice your Wolfram language skills. And to be honest, most of the data sets that you find on the Wolfram Data Repository are like that. So Just a quick aside, if you're ever experimenting with some data analysis function in Wolfram language, a very sensible thing to do is to just go to the data repository, import something, um, and then play around with that instead of using data from elsewhere and having to clean it up and so on. But anyway, okay, let's move on. Oh, before I move on, just one thing I should mention. The structure of this object that you're seeing here, this little table, is a dataset. And a dataset is just a different representation for a few underlying structures. And you can get the actual underlying structure of the dataset by wrapping the dataset in this normal function. So in this case, we have a list of associations where each row in the dataset is a association in the list of associations. So if you prefer to work with the row format of the data, then you can always wrap it in normal, regardless of what the underlying structure is, and you will get that underlying structure. Okay, so just see a question in the chat. Rui is asking, there's a resource object unknown error when downloading. Is it just me? I'm guessing you mean when you are running this resource data function. This might be a network error. It sounds like it. So if you just try it again, hopefully that should work. The other thing to see is if you are if the name of the data set is correct with all the periods and all the spaces and all of that. If in doubt, you can go to the Wolfram Data Repository website and you can copy and paste the actual function that you need to run to get to the data set. But let me know if you're still having problems with that, and um, we can try to solve that. Um, okay, so let's start visualizing data. So probably the most simple way we can visualize data is by including it in a grid. So a grid is a function to organize a list of data into a table-like layout. So it's not a real table, functionally speaking, but it looks like a table visually. So this is just a for very, very quick visualizations. So here we're using some sample data. So we're not dealing with the big data set object at the moment. We're just using a list of lists um, with some data that is structured in the same way as our big data object. But just for the sake of simplicity, we're defining it in line. Um, so you can have grid values where each list is, you can think of it essentially as a row in the grid, and you can take and you can have a list which is the header rows, and you just include all of that into the grid function, and you get this very simple, very basic table-like visualization. Again, this is you're not going to use that when you're communicating your results or when you're publishing something. This is just very quickly if you're working with some data and you need to see roughly what it looks like. Just put everything in a grid, you get an idea, and then move on. One specific benefit of grid that is actually not present in most of our other visualizations is that this could be converted into text. So if you're using LaTeX, it's very commonly used in mathematics, physics, things like that, and you want to convert some Wolfram language data object into text form, so you can paste it in your text editor, text renderer. Um, Grid is the right tool for that, because um, you can call this function called text form. You can pass it your grid, and then that generates the actual text code that you can then copy and paste and get that. But other than that, as I mentioned, it's just a quick and handy function to just visualize data simply. So let's actually start looking at slightly nicer visualizations, and let's actually start dealing with our data set. So as I mentioned, for the different visualizations, we will be slicing the data in different ways. So the first way we're going to slice the data is that we're going to load the top 50 names per year. So just to go back to how our data is structured, we have the popularity of different names per year. So Here, the first way we're slicing the data is we're asking, for example, for the year 1984, what are the top 50 names specifically for that year, whether male or female. So that's our first slice of the data, and we'll see what that slice looks like. Um, all of these slices are kind of predefined at the end of the notebook. So as you see here, I'm calling this variable called genderless top 50 per year. We haven't written this here anywhere ourselves, but if you're interested in how the data is sliced, you can go all the way to the end of the notebook, and that will give you well, in this case, it's just imported from a file, so that's not very interesting. But when we get into some of the helper functions and some of the other slices later on, you can find the way they are sliced here at the end of the notebook. But again, we are focusing on the visualization. So for each example, I'll basically be explaining what the slice represents. We'll see what it looks like, and then we'll visualize it. So for our top 50 names per year, this is what our slice looks like. So it's an association, which goes to an association. So the key of each association is the year. So let's say 1936. And we see that the name Robert is the top one name for that year because it has 58,670 people. Then for the year 1977, rank one name was Michael, which had 68,000 people in the dataset, and so on. And so we have this association structure for each one of the years in our dataset. And I believe the years go from 1910 to 2012, something like that, if I'm not mistaken, or maybe a bit later, 2015, maybe something like that. But we have quite a big range. So here we are getting the top names for each one of the years. Sorry, not only the top names, but we're getting the top 50. So for year 1936, the top name is Robert, but we also get the rank 2, the rank 3, and all the way up to 50, which in this case is Walter. Okay, so we have our slice. Let's see what we can do to kind of visualize it so we can get an idea um, of the top 50 names. So I'm just evaluating the code. So here we're using a helper function, which again is defined at the end of the notebook in the initialization cells. And this strips the ranks over the years. So this helper function takes a name, in this case Mary, and it just gives us the rank of the name Mary for each of the years in our data sets. So again, we can see you can see what the data looks like. So we see for the year 1910, Mary was ranked number 1. 1911, Mary was ranked number 1, and so on, all the way to 2014. So once we have that little helper function, then we can start visualizing. So here we're using 4 different visualization functions for the names Mary and the names John. So we are interested in how those two names, how the popularity of those two names changes over the years in our data set. So we're using 4 different ways to visualize it. We're using list plot, list log plot, list line plot, list step plot. So they're grouped together because they're all very similar. So list plot just or you may know it as a scatter plot, but it just plots. It has an x-axis, which in this case is the years, the year in the data set, and it has a y-axis, which in this case is the rank that the name takes. So if we hover over one of the points, so we can see that for year 1910, the name John was ranked number 1. So the dot is plotted there. And we can see that immediately from this visualization, we can see that the rank for the name John goes higher and higher as the time period goes on. So the way to read this visualization is that the name John gets less popular relative to other names, obviously, as time goes on. So it was very popular in the 1910s, 1920. In fact, it was the most popular name. But then as you go to the 1960s and beyond, it becomes much less popular. List log plot, same idea, just logarithmically scaled. So you have a a different way to visualize. Logarithmic scaling, again, it's a broader topic than this webinar, but you can use logarithmic scaling to kind of normalize if your data is highly skewed and things like that. So you can see it in a different way. List line plot, same idea, but the dots are connected by a line. Not that interesting, or it is probably one of the most common functions you use. By not that interesting, I mean that it's not telling us much more than the list plot itself. It's just a matter of how you want to visualize that list plot, whether you just want the dots or you want them joined by a line. And list step plot, again, almost identical. It's just that the differences are plotted by these kind of more discrete steps instead of a more smooth line. So that's one example of a very simple way to visualize a slice of data. And you can see that immediately you get a much better sense of how, well, in this case, we're looking at two names, how the names John and Mary grow in popularity or don't grow in popularity than you would get just by looking at the numerical data. Okay, so let's keep going. Let's take another question now. So the question we want to ask now is, how has gender amount changed over time? So we're going to load all the data that includes all name use by gender by year. So in this case, we are going to be looking at a very similar data structure. Again, we have the year as the key in the association, and then we have the value is how many female names there were in that year and how many male names there were in that year. So here we are dealing with, again, with dates as the keys. So the way to visualize dates is they're kind of corresponding functions. So just like we have list plots for normal values, we have date list plots when the values are date objects. So what we're seeing here is a grid of 4 plots that are basically mimicking the grid we had previously, but this time we're visualizing just in total male and female names. So the blue line represents male names, or I guess male birds in this case, basically, and the orange line represents female names. So not very informative because obviously they're very close. But this is the way you can visualize data objects. So if you have normal numerical data, you would use list plot. If you have date objects like here, you would use date list plot. And it just works the way you would expect it to work. And again, we have the same date list plot, date list log plot, which is logarithmically scaled, step plot, which is a more discrete visualization. Oh, stacked date list plot is a bit different. So this, I haven't really found a very good use for stacked date list plot. And the way to read that visualization is a bit weird as well, because here the orange line actually represents the total, and the blue line represents of that total how many were the male names. So basically the area of the orange blob should be roughly the same as the area of the blue blob, because they're roughly the same here. Yeah, probably not the best visualization for this type of data, because if you show this to somebody, they might read it as, oh, actually there were so many more, there are twice as many female names as male names, but this is not actually what the stacked date list plot is showing. They're just stacked on top of each other, basically. It's not showing you relative differences unless you compare the actual area. So, but anyway, it is an option if you do find a use for it. It is visually appealing, but yeah, it's just a bit harder to read. Okay, so the next type of plot we're going to be showing is timeline plot. Timeline plot again takes date objects, or specifically date intervals. So we are going to be using again a a predefined variable. So the rank one changes function, again defined at the end of the notebook, it determines the year intervals that a name was ranked number one. And when we have these timeline intervals, we can use a timeline plot function, passing our intervals and defining the range. So easier to explain by looking at the resulting plot. Let me make this a bit bigger. So here again on the x-axis we have all the years in our data set, and on the y-axis we have different brackets essentially for the different names. And what we are visualizing here is which periods did that name rank number one. So if we look at the bottom bracket, which is Mary, we can see that Mary was the number one name in the period between 1910 and 1930, and then in the period of 1932 and 1934. So there was 1931, Mary was not ranked number one, which is why this little plot, this little line here is broken. In 1931, the top ranked name was Robert, and so on. For each name, you can see the interval in which it was ranked number one. So you can see that it's actually there's actually not that many names that have been number one in any period. It's basically a very short list of, what is it, 10 different names. So between those 10 different names, you have all the number one ranks for our period. But timeline plot is, again, another very nice function dealing with intervals. You'll see it a lot if you're dealing with historical data. So you can use it to plot historical events. So for example, you could pass it, I don't know, the World War II, and you'll see a nice little timeline plot that shows you the start date and the end date. But basically, you can use it for any date intervals. Anything that starts on a date and ends on a date is probably the best represented in a timeline plot. Then we can take some categories. So obviously, pie charts, bar charts, very common ways of 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 defining categories. Um, So here we are loading a different slice of data that includes all name used by gender over all time. We can see what the data looks like. Um, so here we are basically we are aggregating by the total number of babies born with that name, regardless of which year they're born in. So the name Serafino, for example, has been given to 52 people across our time period. So we don't actually care which year this name was given. We just want to take the total. Japheth was given to 5 people, and so on. Obviously, some names are unisex, and that's another slice of our data, and we can normalize that. So, for example, the name June, obviously mostly given to females, but there are also 779 people, 779 males also named June, again, across the duration of our data set. So in this section, we're not really caring about the years. Cool. So how do we visualize that? So gender is a categorical description. A pie chart visualizes the proportion of different categories around the disk. So we're getting the top 20 male names across the whole period. You can see James is the most popular one, 4,009,900,000. Then it's John, then it's Robert, Michael, and so on. So how does that look like on a bar chart? Sorry, on a pie chart, not on a pie chart yet. So here we are producing two pie charts. One is for the male top 20 names, and the other is for the female top 20 names. We're taking top 20, but we also have this special category called others, which groups all the other names, so all the names outside of the top 20. So let's look at let's see what this actually looks like. So pie charts are interactive in Wolfram Language. So if you click on the different sections, they pop out in this nice way. So you can kind of highlight different sections as you talk about them. So the first thing we notice on the pie charts for the male names is that obviously the other category makes up the bulk of the pie, so to speak. So even though these top 20 names are very popular, um, relative to all of the names, all of the different names given to people, they really don't make up that huge of a portion of the pie, so to speak. But we can see that, for example, the name James. If we collapse this, so this is the name James, you can see that it makes roughly probably less than 5% of the whole pie chart. And you can see that for each one of the different names in the top 20 for men. Same thing with the women pie chart. So, but having them side by side, the men and male and female names pie charts, we can immediately see some interesting differences. So, one difference we can see right away is that the top 20 names for males make up a larger portion taken together of the pie chart compared to the female top 20 names. Effectively meaning that there's more variation in names in females than males. Another thing we can notice is that the top one name for females, which is Mary, is much more popular than the others in the top 20. So you can see that the slice for Mary is much bigger than the slice of Patricia, whereas with the males, the slice for James is roughly equal to the size of John. So that tells us that the name Mary is disproportionately more popular in females compared to other female names, of course. So again, a few kind of insights that you can get by visualizing. I mean, you can see that in the numbers as well. So you can see that the numbers for James and John are very, very similar. Um, you can combine pie charts. You can kind of stack them. So here we can see again, now we're taking some example data that were customly defined, but you can see that you can have an outer pie chart and an inner pie chart that represent different values. That's again another kind of a situational visualization option, but it's an option that's available to you. And for the pie charts, you can also have them in 3D. So if you want to rotate them for any reason, that is available, and you can still click them to kind of expand and so on. Okay, so another way to visualize kind of categorical variables are bar charts. So again, let's define our data and let's produce the charts and let's look at what they are telling us. So instead of looking at proportions, because pie charts, the charts that we were just looking at the moment, are mostly useful for seeing proportions. That's why we were able to see that the top 20 names, even though they're very popular in the grand scheme of all names for that gender, um, don't really make up that much of the total. Um, Instead of looking at that type of information, bar charts allow us to examine total values per category. Again, we have a 3D option, which is exactly the same, just styled differently. So let's look at the normal bar chart, which we have here on the left. And again, it gives us the top 20 names. This time we don't have an other category because the bar for that would be far higher. But we are only looking at the top 20 names. So you can see that James and John, this is probably a better way to kind of visualize the differences uh, between the different names. You can see the bars for James and John are very similar. But if we do females 20, you'll see that the bar for Mary is much higher than the bar for Patricia, which is the second name. So that's oh, actually, let's have them side by side again because I quite like the previous example. So let's do that. Here we'll do males 20. So again, this is probably a better visualization of the point I was making earlier that the name Mary is much more popular than the other popular names for females compared to the name James for the male female for the male names. Um, Then we can have these paired bar charts, which you have one set. So one way to kind of visualize two bar charts is to have them in a row like this, like we just did. Another way to do that is to have them vertically side by side. Um, but this is essentially giving us the same information as this. Um, in this case, with this specific data, it's a bit nicer because you can have the name on top of the relevant bar, and you can have the name horizontally, because if I wanted to plot the names here, which I could, the name would have to go kind of above the bar, maybe vertically, or yeah, there's not really a clean way to kind of include that information. Whereas with the paired bar chart, that's nice, but essentially the information and the visualizations themselves are the same. Okay, let's keep going. We have a few more kind of basic visualizations that we can go through before we get into the more complicated stuff. Um, Histograms. So histograms are very useful for looking at distributions. So what is a distribution? In the length of all names. So here we'll be taking each name and we'll be looking at how many letters that name is. So histogram visualizes distributions by counting frequency of values and organizing the counts into bins. By default, equal bin widths are chosen. Anyway, these are kind of details that are not that important at the moment. But the basic idea is that you can customize pretty much everything about any visualization that you see, and how you actually customize it we'll get to a bit later on. So let's look at what our current slice of data actually looks like. So here we're taking a names variable where we have only extracted the actual names. So we don't care about the state they're born. We don't care about how many people were born with that name. We're just looking at all the unique names in the dataset, which are 30,000 and a bit more. So we have essentially a list of length. We can check very quickly. Length names should give us how many names we have in our dataset. We have 30,000. 274 unique names in the dataset. So what we're going to do is for each name, we're going to count how many letters are in that name. And the idea is we want to see what is the most common name letter length, if that makes sense. So that's very easy to do once we have our list, and then another list where instead of the name, we just get the number of letters that go into that name. So you can see that for the name Aben, we have 5 letters, the name Aiden, 5 letters, and so on. So again, we don't care about popularity here. We're just taking each name as its own thing. And then once we have the list of counts, we can pass that to a histogram, and then we can visualize what that information looks like. So we can see that it is the name with 6 letters in them that are the most common in the dataset, followed by the names with 7 letters, followed by the names of 5 letters. So it seems like you have this rough kind of a normal distribution around the number 6. So it seems like 6 is the sweet spot for letters in a name in the US. Just like we had a paired bar chart, we can have a paired histogram. Again, the same idea. You're looking at two different histograms side by side. Um, so same type of visualization, just combined into one. Then date histogram, again, just like we had line plot and then we had date list line plot. Here we can have the date version of histogram, which is date histogram. So again, here we're using a helper function, which is again defined at the end of the presentation. This gives us the year a particular person with a given name was born. So in this case, we're taking the name Abby, and we're seeing for each year how many Abbeys there were in the dataset. So again, this gives us an idea of the popularity of one specific name across the time period. So you can see that for the name Abby specifically, it was not very popular in the early early 20th century, but it became much more popular towards the end and into the new century as well. And you can replace that, obviously, once we have the helper function, you can replace that with any other name, and you can visualize that as well. But again, because because we're dealing with date objects here. So on the x-axis, we have date objects. We're using the date version of our visualization, which in this case is date histogram. Um, and then the other thing we can do is we can use smooth histogram. There's no date version of the smooth histogram, so you would need to convert each date object into an actual number, which obviously you lose a lot of a lot of information that way, because with date objects you can actually do arithmetic. So you can say add a month and 30 days to this date object. You can do things like that. Whereas if they're just pure numbers, then you can just add other numbers to them. But anyway, if we want to use the smooth histogram, which is this kind of a nice smooth line, then we can convert those data objects to numbers, and then we get um, a similar looking kind of visualization for that name. Um, Let me just abort this. Okay, so what about when we just have pure text data? So far we've been visualizing numbers, we've been visualizing dates, and that's pretty much it. What do we do when we want to visualize text data? One option is to use a word cloud. So here we're looking at the top 50 names, I guess, again across the whole period, and we want to visualize that just so we can have a better idea of how popular, which are the names and how popular they are relative to other names. So one nice option that I'm sure you've seen in many places before is a word cloud, where um, each word that you see in the word cloud is a name from the top 50, and the size of the name corresponds to the popularity of that name in that data set. So the name Robert, for example, is much more popular than the name Amanda, and you can see that because Robert has a much bigger font size effectively than Amanda. Very popular kind of a marketing type visualization, but it can look nice depending on the data that you have. And word cloud is quite flexible. It takes it takes arguments in different ways. So in this case, we are providing it with some associations, where the key is the name and the value is the actual number, and it uses the number as kind of the weights for the size of the word cloud, the size of that word in the word cloud. You can just provide it simply with a list. So let's say um, if you're dealing with smaller data, let's say Mary, there were 5 people named Mary, you can just provide the word cloud with a list that is like Mary, Mary, Mary 5 times. So it accepts the data in different ways, and you can read the documentation if you're interested in creating this specific visualization. And then probably the last thing I'm going to cover in this notebook, because I'm quite eager to move on to the next ones as well, because there's important stuff there. But mentioning geographics is also quite important. So far we've been visualizing numbers, date objects. Now we visualize strings. So what do we do when we actually want to visualize geographical data? We have again a wide array of geographical visualization functions. So let's look at some of them. For that purpose, let's slice our data in different way, in a way that's going to include geographical information, obviously. So here we are looking at the usage state. We're looking for the top 20 names. Wait, let me see what we are looking at for the females. Oh, I see. Okay, so here we're kind of bifurcating by gender, but basically, let me tell you what each of these associations mean. So we are taking each names in the top 20 for females. So Lisa, for example, is in the top 20, and then instead of looking at the total number of Lisas in the United States, we're breaking them down by state. So we're saying in Alabama there were 1,200 people named Lisa. In Alaska there were 1,400, and so on. Then for males, we are looking at the 2,000 least popular names, again broken down by states. So, for example, the name Tonya uh, was given to 5 people in the state of Tennessee. Drayden was given to 5 people in Texas, and so on. So the main point here is we are actually including some geographical information, which are the different states. Now you see that the states are these kind of orange boxes which represent entities in Wolfram language. And the point of entities is that it's not just a simple string that doesn't mean anything, but the entities actually carry a lot of information in themselves. So we obviously have the name of the state, but in the Wolfram language entity for, let's say, Alabama, we have the geographical information for that state as well. So where to plot it on the map if we need to plot it. So we can kind of leverage that built-in information to produce some geographical plots without needing to manually specify coordinates or positions on the map or GPS or anything like that. We can just pass in the state, and we can and Wolfram language knows how to extract the geographical information from that state and how to plot that geographical information on the map and so on, which makes especially yeah geographical plots really easy to work with in Wolfram language. So let's see what we are doing here. So here we're using a function called geobubble chart, which is the first one in the column. And here we're taking a single name, so in this case Mary, and we're seeing for each state how popular is that name for each state. And again, the size of the bubble, so there's a bubble centered on each state, and the size of the bubble determines how popular the name Mary is in that state. So my US geography is not amazing, but I'm guessing this huge bubble here on the West Coast is California. So we see the name Mary is much more popular in California than it is in the neighboring state to California, which I'm not sure which one that is. Um, Again, this huge bubble here must be Texas, and so on. It gives you an idea of the um, relative proportions of the name Mary in the different states. But instead of just outputting just plain text, you can kind of visualize it on a map. Now, because these bubbles are quite big, when you get to states here, you probably couldn't tell which is which, but depending on the type of data you're using, this might make sense. But if the bubbles are too tightly stacked, you could use another common geographical visualization, which is georegion value plot, where you pick a color and then the intensity of that color represents the popularity of that data in the dataset. So here, if we look at the more kind of the more red a state is, that means that the name Mary is more popular in that state compared to other states. So again, I'll pick California and Texas because they're easy to identify on the map. So we can see that the name Mary is much more popular in those states compared to the states between them. Cool. So we have some more information in this notebook about tabular, which is our new way of representing tabular data. It's very much worth getting into because tabular is more efficient and there are some nice things that come along with it. But we probably don't have time to do that in this webinar. So this is more about data representation, and I would like to focus on data visualization because, well, that's what you're here for. But it is worth mentioning that there is a different way of structuring tabular data. But many of the, if not all, hopefully all of the visualization that we've seen here work both on tabular data as well as on dataset. So it really is just a matter of how that data is represented for other purposes, specifically for data analysis. If you're doing some heavy data analysis where you need to transform your tabular data, then going with tabular makes much more sense. But as far as visualizations are concerned, it is basically the same thing. Just slice the data in however way you want, and then you're able to use the visualization functions directly. Let me just see if there is anything else worth getting into here. There is a nice table at the end of the first notebook, which which you can use kind of as a reference point if you know what what structure your data is in. If it's two-dimensional or three-dimensional, it lists a few different Wolfram language functions that can be used to visualize that type of data. We covered some of them in this first notebook, but obviously we didn't have time to cover everything. So if you know that you have, let's say, three-dimensional data, you can use this to see, and if you hover over the function name, you see what that looks like. So it's quite a nice kind of, again, a reference sheet more than anything else. Um, but I think that's it for this notebook. Mm, Hopefully, it gave you an idea of kind of the most basic types of visualizations. If you're dealing with numbers, text, dates, or geographical elements, there is a basic visualization functionality for all of them. Cool. So let's move on to um, I'll move on to notebook number 3. So as I mentioned in the beginning, um, these notebooks contain very useful dynamic elements like this one here, which it's not worth spending a ton of time on them at the moment, but I would like to show you how they work so you can use them as references later on when you are producing your own visualizations. So one of the points, one of the good things about visualizations in Wolfram language, other than them being integrated in the language, and you don't need to import any external libraries or things like that. Another thing, another very useful feature of those visualizations is that you can customize pretty much every element that goes into making that function. So as you saw in the first notebook, we were using functions directly. Just use histogram, for example. We pass in the data. We don't specify how the bars are rendered, what color they are, what size they are, what width they are, what the axes look like. So we didn't include any of this. And when we don't include any of this, Wolfram Language just gives us a reasonable kind of approximation, just reasonable defaults that make our graphics interpretable. But if you're using visualizations for communication, in many times you want to go into a bit more detail. You want to customize different aspects of your visualizations. And as I said, it's a good feature of all of those visualizations is that they're very customizable. You can pick any single element um, in that visualization and you can customize it. But that has a downside in that the code can get quite complicated, and there's no real way around that. If you have the freedom to customize everything, then by necessity almost, then the code can end up being very complicated. So these little dynamic elements that you see, well, we see one of them on the screen here. Um, these give you, obviously, all of the different customization options are documented, and you can read the documentation, and they're very understandable. But if you want a more visual kind of a way to play around with the different customization options, then these dynamic elements are really useful. So let's look at here. We have our list plot where we have plotted some numbers on a list. And on the right of each of these dynamic elements, we have different customization options that we can play around with, and we can see immediately how that affects our visualization. So the first thing we can do is we can remove the axis. Obviously, if you don't want a horizontal or a vertical axis, you can remove that. You can remove the ticks on the axis themselves, so the actual labels, if you don't want those. You can give each one of those a title, or you can not give them a title if you want, and you can change their point of origin. So where do they start? So you can have it starting at the top right, for example, or the top left, or any other point in between. So the real useful thing, other than immediately seeing, let me make this a bit more normal. The other useful thing, other than seeing how these options affect your visualizations, is that when you do some customizations here, let's change this again, for example, give this a title, we remove the ticks. So this is by no means a good visualization at the moment. I'm just changing different things just to show that you can customize them. But the real useful thing is that for each customization that you arrive at, so let's say I customize all of these things and I think this graphic looks perfect at the moment, which it doesn't, but anyway, imagine that it looked perfect. Instead of searching for the documentation, searching through the documentation for the code to produce that, I have the code right at the bottom of the dynamic element. And as I change something in the graphic, then the code updates. So this is really, really useful. Um, you, when you're producing a visualization, you want to change a bunch of things. You come here, you look at your dynamic element, you change all of this, and then you have the code, and you can copy, or essentially you can plug in your own data in that code, and you keep all of the customizations right there. So this specific dynamic element is for a list plot, but we have dynamic elements for pie charts, for bar charts, and all sorts of different things uh, that you can use. Um, but all of those work exactly in the same way. They give you a nice user-friendly menu of all the different things you can customize. Um, and then once you have finished customizing them, they give you the code that is used to produce that. So you can essentially copy the code, uh, paste it in your notebook, replace replace the data with your own data, and then you keep your customization options. So yeah, we have those dynamic elements for pretty much every single one of the basic visualizations that I showed you in the first notebook. So yeah, again, my advice with those would be just save this notebook somewhere on your computer, so you know that whenever you are producing a visualization, you can come to this, you can modify it, and you can get the code much easier than going through the documentation, as nice as it is. Okay, so I'm not going to go through all of them, and again, the other notebooks, 3, 4, 5, contain similar things. So the previous one was for labels. This one is for arranging elements, which is another thing you can customize quite a lot. Um, but yeah, those are very useful resources to have. And with that, I shouldn't have closed this. Give me a second. Let's look at the actual final notebook where we'll be using, instead of using built-in visualizations, we're going to be using graphical primitives to build our own. So let me just open that. So this is notebook number 6. And here we'll be constructing, well, there are three examples in this notebook, but I like example 1 and 2 the best. And we're probably not going to have time for 3 anyway. So let's focus on 1 and 2. Let me just make that a bit bigger and let's get into it. So yeah, just reading the introduction, now that you know the ins and outs of basic visualization, you can create some eye-catching visualizations. Um, okay, let's get into the first example where, just to show you what we'll be working towards this nice kind of bubble chart with corresponding bar chart. And we'll see what that visualizes in a moment. Um, Okay, so here we're going to be, and yeah, again, we're going to be producing a few interactive charts that make use of literacy, life expectancy, and population data for different countries. Again, all of that data is built in Wolfram Language, built into Wolfram Language, so you don't need um, to go externally to fetch it. And the final result will be a bubble chart of life expectancy against the literacy for each country, along with a bar chart for the population trend for each country. So we're taking um, a lot of different data, and we are trying to kind of summarize it visually using a custom visualization. So the first thing we need to do, obviously, is get all of the data. As I mentioned, all of that data is built in. Um, so the way we get it is using this country data, which can give you a lot of different things about country entities. So in this case, we're interested in literacy fraction, life expectancy, population, and the continent in which that country is. and we're getting that for basically every country in the world. So if this was for the UK, then the continent would be Europe. Population will be whatever 66 million or however many people there are here. Life expectancy will be what it is, and literacy fraction as well. So all we need to do to get the data is this little kind of loop construct here. And then we're just deleting any missing values, which probably, hopefully, there shouldn't be any missing values, but we can do that as well. And we can visualize an example of the data, see what that looks like. So, for example, for Turkey, we have this would be the literacy fraction, um, which the way I'm reading it, this is 96%. Life expectancy is 77, almost 78 years, um, and the population is 85 million people. Continent is Asia, and so on. For each country, we have this corresponding values. So that gives us again a nice little data set that we can work with. Um, so the first thing we can do is we can use a bubble chart to produce kind of some standard visualization for that information. So here we're creating a bubble chart where on the x-axis we have the literacy rate, which goes from 0 to 100, obviously. On the y-axis we have the life expectancy, which goes from 50 to 100. And then the size of the bubble represents the actual population. So you see that, for example, this bubble here, this big bubble, represents a country that has a literacy rate of about 75 to 80%, life expectancy of 70, and it has a huge population represented by the size of the bubble. At the moment, this is not interactive. We couldn't do anything. We couldn't point to any of the bubbles to see what the countries are. This gives us a nice starting point. The next thing we're going to do is we are going to group that data by continent. So then, as well as all the information that we have in our previous bubble chart, we're going to add an additional kind of visualization element to that chart, which is the color of the bubble. So, if we look at the resulting bubble chart again, we'll see that some bubbles are differently colored. So maybe the blue bubbles will be representing Africa, the green bubbles will be representing Europe, and so on. So again, this is adding a bit more information into our visualization. But so far, again, this is not interactive. We don't exactly know what is happening here, but we're adding more information. Um, so one way to actually know what's happening here is to add labels to the side. And we do that. I'm kind of glossing over some of the code here because it's not really that interested. I mean, for example, the labels here um, are just chart legends with the different continents. So instead of getting kind of line by line in the code, I would rather kind of walk you through the what the vision for the graphic is, and then if you're interested in the code, you can kind of find it here. And if you're using this with your own data, it will be just a matter of replacing the variables. So that's not really the most interesting thing here. It's much more interesting to say that when we have that visualization, we need a legend, and the actual methodology of getting that legend. It's a bit less interesting, but it's there for your reference. Um, so now we have our bubble chart with legends. So we see that the blue circles, the blue bubbles, are indeed Africa. Um, the yellow ones are Asia. Green ones are Europe. There's an interesting outlier here, which is in Oceania, but we don't know which one that is yet because we couldn't hover over it, and we'll add that a bit later on. Um, so let's run this. So here we're adding two tips. Um, so we're changing the two tips from the bubble from the population to the country name, and that should give me the ability to hover over them, which I don't have at the moment. So I wonder if there's something wrong with the code. The basic idea here is that when we hover over a bubble, we should see the country name that the bubble corresponds to, which in my case doesn't work. Let me just have a quick scan through the code to see why not. Maybe it will be fixed in the next example. Um, so let's have a look. Here we're doing a bar chart of the population. Obviously, the bubble sizes are proportional to the population, so it might be interesting to see how the population changes over time. We can get that information by using Wolfram Alpha from within our notebook. Um, and we can also project in the future, so we can use Wolfram Alpha to do projections not only for historical data but also for dates in the future as well. So here we are projecting up to 2030, which is not that far into the future anymore, to be honest. But we get a list, and we can see what that looks like. Um, what that looks like on a bar chart, of course. But I'm kind of curious about the bubble chart. Here we're doing some styling on the bar chart, so we can have labels on top, labels on bottom. You can have you can have a plot title. All of those are covered in the notebooks that we kind of glossed over. But if you're interested in customizing all of those, again, there's nothing really that special about them, but there are a few kind of options that have weird syntax. So if you're interested in those, you can look up the documentation or the previous notebooks. Um, Again, we can style individual bars. So because the data for 2030 is estimated, it's not actual factual data. We can have a visual kind of representation of the fact that it's estimated by shading it in a different way and having text. Again, that is basically another option that you can pass to the bar chart visualization. Let's see what we're doing here. So far we've produced one bar chart, but we can abstract that into a function, and then that function can take any country, and it can give you the same bar chart for each country. So here, once we have defined a function, which is here, then we can pass in any country and get the same bar chart. So we can pass in Uganda, and we can see how the population of Uganda has changed over time and how it's projected to change in 2030. Likewise, for France, we can see a different population growth profile. Um, so now we're back to our bubble chart, and let's see if this is going to work well for me. Um, we can add additional data by breaking down the information on a per gender basis. So here we are grouping the data by continent again, and when we look at the table, we see that there's an additional column here, which is the continent. So you can see, for example, you can split the data by different continents. So let's say if you're only interested in looking at African countries, then you can do that as well. Um, Then we can add that information back into our bubble charts, which will give us this. Again, this is a huge piece of code that we don't need to get into details again, but let's look at the end result. And again, if you're interested in the end result, then you can look at how the code works that produced it. It should be pretty self-explanatory. And finally, here my hover tooltips are working now. Um, well, I get it. Yeah. So when you hover over a bubble here, you can see all the underlying information from that bubble, except the actual country name, which should appear on hover, which it doesn't for me. I'm pretty sure that's some bug in my current setup. if you're following along with the notebook, when you hover over this bubble, for example, you should get a little tooltip that says that actually gives you the country name. But aside from that, it also gives you the underlying information about literacy rate, life expectancy, and population. So if I hover over this little bubble here on the top left, um, you can see in the corner, I can see the literacy rate, which is about 50%, life expectancy, which is 75 for males, 81 for females, and the actual population. So this is a very small country. I wish I knew which one it was. Um, but yeah, basically we have incorporated. So in the previous step, we broke down the underlying data by gender, and here we've incorporated that breaking down into our actual tooltips. So we can see what for literacy, life expectancy, population, we can see how that breaks down by gender for each one of those bubbles. So now we have all the different elements. We can put everything together into one big graphical element, which essentially has two visualizations stacked on top of each other. So we have our bubble chart where we can hover over and see information about each country. So again, to kind of summarize, on the x-axis we have literacy rate, which means that if a bubble is more to the right, that means that the literacy rate in that country is higher. We have life expectancy on the y, meaning the higher the bubble is, the higher the life expectancy is of that country. We have the size of the bubble, which represents the population. So the bigger the bubble is, the more populous that country is. We have the color of the bubble, which represents which continent that country comes from. So yellow bubbles represent Asia, blue bubbles represent Africa, and so on. And in addition to all of that, when we hover over a country, again, you should see the country name. I don't, but you should be able to. And on the top left, you have a mini table that breaks down all the underlying information by gender. So you can see that in a single visualization, we were able to pack in how many, maybe 4 or 5 different variables, which again is very useful for communication purposes, especially when you're trying to communicate so many different things um, in one visualization. And then the other thing we have is our bar chart that we constructed, in this case for the United States. So we can see how this is in millions. So in 2020, there were 339 million people in the United States. In 2030, the projection is 356, and we have this visual indicator that this is a projection by shading it in a different color and having custom label in that. So this was one of the examples how you can, and the basic idea of this example is you can take graphical primitives and combine them into your own custom plot. So there's no Wolfram language function that produces this nice bubble chart, but you do have bubble charts and you do have tables and you have tooltips and you have different coloring options. So you're able to take all of that and put it together into one kind of coherent visualization, which is also what we're going to do for our next and final example in this webinar. Um, Here we are back to our baby names dataset, and we are going to I think in this case it might be useful to show you the final visualization first, and then see the steps we need to take to get there. So let me just evaluate all of that so we can have the final visualization. Look at that first, and then see how we get there. All right, so this is what we are working toward in this example. So this is a completely custom visualization. There's nothing like that that is built into the Wolfram language. It is this kind of a slightly more complicated graphic, a visual history view as baby names. And basically, we are taking the most popular names, so names like Mary and Robert and John, and we're plotting the range of of years that we have in our data sets. So again, this is from 1910 to 2015. And we are seeing how, so this is on the x-axis. On the y-axis, again, we have the brackets with our names. Um, and in the body of the plot, we have the intervals in which this name was in the top two in this case. So whether it was rank number one or rank number two. And the color represents the actual rank. So the darker the color is, the higher the rank is. The lighter the color is, the lower the rank is. So we can see that for the name Emma, for example, it was rank around 50 at the beginning of the 1910s. And then it really surged in popularity after the 2000s. And here we have another column of values, which represents how many years that name was in the top two. So we can see, again, let's take the name Emma, for example. In addition to all of the other information, we can see that the name Emma was in the top two for 3 years in our whole period, whereas a name like Michael, for example, was in the top two for 54 years in our period. So again, we are the main point of this is we're trying to condense a lot of different types of information into a single plot. And to do that, that's going to be highly dependent on what your data looks like under the hood, so to speak. Depending on your data, you need um, different ways to visualize it, and Wolfram Language gives you the primitives to do that. Oh, and in addition, we have a nice little menu here where we can select a different name and add another bracket to our plot. So this is kind of a bit more interactive. So if we're interested in the name Frank, we can add that. We can click on the button here. We can add that. And we can see that even though it was quite popular up until the 1950s, really, it was never in the top two names in the United States. Cool. So that's the end goal. So let's look at how we get there. Um, this is where we start. Um, we already know about our baby dataset, so we don't need to do that. So obviously, the first thing we need to get the top two names for every year, because that is basically the core of the data that we are visualizing. So we need to slice our data in such a way to get the top two. Um, so this is just the way to slice the data. This is more of the mechanics of the actual thing rather than anything interesting. The next thing we're going to do is we are going to color by ranking. So this is how we are going to get that nice color gradient where a darker color represents a higher rank and a lighter color represents a lower rank. So the way we do that is we use this blend function. And again, I believe blend, just to say what blend does is it takes a list of colors and it generates a gradient that goes through all of these colors. So here we're taking, so when the value is 0, we are taking this dark purple color. When the value is 1, we're taking this light yellow color, and then we have a few colors in between. So we're asking Wolfram Language to generate a gradient that goes through all of these colors based on the value. And then we can apply that gradient to a normal list plot so we can see how that works. So that's all good. And then we are, again, there's a little bit of color manipulation here, which again, if you're interested, you can look into that. But essentially, we want to generate this color gradient graphic that we're going to use for the legend. The next thing we're going to do is we're going to define a custom font. In this case, we are using a font Arial CE. You can use any font that's available on your system. And the way to apply a custom font is very simple. You call this style function on whatever text you want to style, and you specify. You can specify a lot of things in style actually, but in this case we are just specifying font options. So we are saying that the font color will be gray, the font family will be Arial, and the text will be bold. So this is what we end up with. And this is how we're going to label the names on the left-hand axis that you saw. The next thing we need to do, obviously, is to arrange things in a grid. So this thing is actually a grid of objects. So you can think of the names as um, the first column in the grid. You can think of the gradients as the second column, and the years in the top two as the third column. So yeah, worth saying that the grid can take any elements, not just text and not just numbers. You can pass pretty much anything to it, and it will just arrange it in a grid. The next thing we need to do is to create our axes. Um, our x-axis, which is going to be the actual the date range for our underlying data. So we have 1908 to essentially 2015. We are adding a little bit of padding here just to make sure that the value is displayed properly. But other than that, this is just, again, the mechanics of how to do that. But the main idea is we want to have an x-axis, obviously. Next, we are creating the actual legend that we're going to append to the top of the visualization. Again, a bunch of code here to do that, but the basic thing is we are using the blend we defined earlier, and we're just uh, putting that blend into kind of a nice descriptive legend here. Um, the next thing we do is we need to add the scales and labels. So here we're doing that, and we're also combining all of the different things that we have produced, all the different individual elements we're combining into one thing. So this column functions takes a list of things, and uh, it just prints them in a column. So if we look at the first thing in the column is the scale, which is this element here. So if you think of the whole plot as one column, the first row in the column is our actual legend. The second row in the column is um, our main visualization, so to speak, which is our grid. And then the third row in the column is our x-axis. Then the final thing we need to do is to add a button, which will give us the kind of the interactive functionality that we need to add names um, to our visualization. So there is a bit of functional thing here, but once we are done with that, it is just a matter of putting it all together. And the way we put it all together is through a mixture of grid calls. So you can see that we're calling grid a few times, and columns. And that is all just to kind of arrange all the different elements, because if we go to the final graphic, each one of those things is a different element that we are essentially putting together into one. Um, so here we want to have a grid where the first row in the grid gives us the legend, the title, and the interactive menu. Then the second row is this, but then inside the grid, obviously, you can have columns to arrange things vertically. So it's just a matter of arrangement, really. But the main idea is that you can have different individual graphical elements, and as long as they work together nicely, you can just arrange them visually together. And even though they're all different elements, they work together as a single graph. And so I think this is it for this webinar. Hopefully, again, we didn't have anywhere near enough time to go through all of the options, but hopefully this was interesting to you to see, one, the most kind of basic built-in functionalities that we looked at in the first notebook. Two, to see the kind of the reference dynamic elements that you can use as kind of a cheat sheet when you're producing your own visualizations for customization options. And three, this final notebook that will show you how you can produce different individual graphical elements using the graphical primitives in Wolfram language, and combine them together to produce something cool. So hopefully all of that was interesting to you. Let me know if you do have any questions. I'll look at the chat because I haven't looked in a while. So if you do have any questions, please put them in the chat. There is one more example here, but we don't have time to go through it. And to be honest, it is not that interesting anyway. We're just producing a plot with two axes. So instead of just having a y-axis, we have an axis on the right as well, which is actually useful, but it's very situational. And to be honest, the final result is not that striking anyway. But if you're interested in that, please feel free to look at that. But this has been it for this webinar. So thank you all for attending. Again, if you have questions, put them in the chat and we can discuss them. But if not, thank you for attending and I hope you have a great day. So let me look at the chat. Ian Williams is asking on YouTube, what style sheet is your presentation notebook using? Is it one of the standard style sheets? Yes, it is. So it's a custom style sheet for WolframU, and it is actually our older style sheet. So our newer webinars use a slightly updated style sheet, but I actually quite like the way this one looks. But yeah, it is a custom style sheet. I'm not sure if it's publicly available, but even if it's not, I mean, you can just get it from the notebook itself. Um, so if you go to Format, Edit Style Sheets, you have all the information for that style sheet. But it is a WolframU style sheet. I don't think, I'm not sure, I wouldn't expect it to be built in here, but it's probably publicly available somewhere on WolframU. Um, Ian, again on YouTube, is asking, can dates for dateless plot be assigned to the vertical axis and values to the horizontal axis? That will be useful for large date spans. In such cases, the date axis may be very long. Yes, absolutely. Yeah, you can invert, you can transpose, you can do pivot tables. You can, yeah, it is. All the visualizations are highly customizable. Um, okay, I'm not seeing any other questions, either on YouTube or Big Marker. So thank you very much for attending this webinar, and I hope to see you in the next one.